Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 18, Scaling and Rotation Matrices. In the previous few videos, we've learned some of the basics of matrix algebra. In particular, we learned about linear transformations. Those are vector functions that satisfy the linear property equations. And we know that every linear transformation can be expressed with a matrix. They're very nice to compute with, but we still have to show that all the different geometric transforms that we're interested in, specifically scaling, rotation, and translation, can somehow be expressed using matrix multiplication. Ultimately, our goal is to be able to give a verbal description and translate that into a matrix. For example, if we want to rotate points around an x-axis by 45 degrees, what's the matrix that performs that calculation for us? That is the goal. And so, in this video, we'll start off with the easiest type of transformation, scaling, and then we'll talk about rotation, and in the next video we'll cover translation. So to begin, scaling matrices are pretty easy to compute. A scaling transformation multiplies every component of a vector by a constant. So for example, here is a scaling transformation that multiplies x by some value r and multiplies y by some value s. And we can pretty quickly deduce that this can be represented with multiplication by this matrix, r0, 0s times xy. Similarly, if we want to do a three-dimensional scaling, let's say we also want to multiply the z component by t, that can be accomplished with this matrix multiplication. It's mostly zeros, but on the diagonal we have r and s and t. And if we scale just by the value 1 in each direction, that's going to give us the identity matrix and the identity transformation. That does not change the value of the vectors at all. And that's really all there is to say about scaling transformations. Rotation transformations are much more interesting to work with. So a rotation transformation, as the name suggests, means that it rotates vectors by some constant angle around the origin. Now, depending on how far away a point is from the origin, the point might move through a greater distance, but each point is being rotated by that same constant angle. Now, unlike scaling transformations, it's not immediately clear what the formula should be or what the matrix is going to be. So our strategy for calculating a formula for rotation transformations is going to be first to present an argument that rotation is a linear transformation, and then we're going to try to calculate the rotation function at the basis vectors. And as we've seen before, those values will give us the columns of the associated matrix. We'll do that for 2 dimensions first, and then once we're comfortable with that, once we learn how that works out, we'll then move on to 3 dimensions. All right, so to see that something's a linear transformation, we have to check to see that it satisfies 2 equations involving scalar multiplication and vector addition. So to start off, we'll try to understand why this equation is true for transformations. I want to see that f of c times a vector is equal to c times f of the vector. So to see why this is true, let's begin by considering the endpoint of the vector v. And let's assume that it's some distance d from the origin. Now if we multiply this vector by c, we end up here. This vector is going to have the same direction, and now this point is a distance c times d from the origin. Now, before we rotate, just let's remember that rotation transformations, they're going to fix the origin point, and they're not going to change the distance of a point from the origin. So we'll go ahead and apply the rotation transformation, which we're going to call f, We'll rotate this vector v, and it will land at this point here. We'll also apply the transformation to c times v, and we'll end up at this point over here. So the results are f of v and f of c times v. Now, again, these vectors lie along the same direction, and their endpoints still have the same distances from the origin. Right? Rotation doesn't change the distance of a point from the origin. So the distance from the origin to f of v, that endpoint, that still has distance d. Then the distance from this endpoint to the origin is c times d. Now, here's the interesting fact. If you take f of v and you multiply that by the constant c, you'll end up with a vector on the same line in the same direction, and the endpoint is c times d units away from the origin. So I can describe this point in two different ways. Right? This point is uniquely determined. It lies along this line, and it has distance c times d from the origin. And so no matter how you get there, if you multiply by c and then rotate the function f, or if you apply the function f and then multiply by c, you're going to end up at the same point. So informally, that's why those two values should be equal. The other property we have to check to see if something's a linear transformation is vector addition. We need to check that f of v plus w is equal to f of v plus f of w. So to begin, I'd like to define another vector. I'll call it u. And let's say u is equal to v plus w. And let's also, just so I can say it more easily, let's call the origin point O. Now, because of the way that vector addition works, the endpoints of v, w, v plus w, which we're calling u, and O, these 4 points form the vertices of a parallelogram. Now I'd like to apply the rotation function to these 4 points in this parallelogram. So rotate the origin, you're still at the origin. V rotates to f of v, w rotates to f of w, and u rotates to f of u. So rotation is going to turn a parallelogram into another parallelogram. And that makes sense. It's not changing the shape, it's just rotating it to a new position. And in particular, right, these are the vertices of a parallelogram, 0, or O, f of v, f of w, and f of u. However, again, by the nature of vector addition, f of v plus f of w should also give us the endpoint of this parallelogram. Right? The points 0, f of v, f of w, and the sum also form a parallelogram. So, since we have 2 parallelograms with these 3 vertices in common, the 4th vertex also has to line up. It must coincide. And so it follows that f of v plus f of w equals f of u. But remember, u is just v plus w. And that gives us the fact that rotation respects vector addition, and so rotation is a linear transformation. All right, this means that we will be able to represent it with matrix multiplication, and to figure out what that matrix is going to be, we need to calculate f of I and f of j. We need to find the images of the basis vectors, and those will be the columns of our matrix. Now, to go through this calculation, we need a little bit of trigonometry, not a lot, just a little. We need the basic definitions of the trig functions. So, given a right triangle, and one of the angles, we'll call that theta. The adjacent side to the angle theta, we'll say that has side length A. The side opposite from angle theta, we'll call that side length b, and the hypotenuse, we'll call that side length h. The sine, cosine, and tangent functions, all the trigonometric functions, are defined as ratios of the side lengths. So in particular, sine of theta is b over h, the opposite side divided by the hypotenuse. Cosine of angle theta is a divided by h, the adjacent side divided by the hypotenuse. And the tangent of an angle is the opposite side divided by the adjacent side. So in this case, b divided by a. So let's keep those definitions in memory, and let's start to figure out what rotation does to the basis vectors. So first, let's consider the basis vector I. And that's the vector 1, 0, since we're working in 2 dimensions. What we'd like to do is rotate that vector up to this new position, f of I. Right, so we're going to rotate that through some angle theta. So we want to know what are the coordinates of this endpoint. Right, so we can think of this vector as being a units across and b units up from the origin. And the vector itself forms the hypotenuse of what is a right triangle. And we know how to calculate the lengths of a right triangle. Right? We know that, for instance, that to calculate this length, right, we can actually use the cosine function. Cosine of theta is the adjacent side divided by the hypotenuse. But dividing by 1 doesn't change the value of the number. So cosine of theta is equal to the adjacent side. And that gives us the first component of our vector. Similarly, we recall that sine of theta is equal to the opposite length divided by the hypotenuse. So sine theta is equal to b divided by 1. b divided by 1 is b. So sine theta equals b, and that gives us the second component of our vector. So what happens to the basis vector I when you rotate it through an angle theta? Well, it becomes this vector, cosine theta, sine theta. And that's the first column of our matrix. The second column, we're going to do a similar calculation, but this time with a vector j. The value of f of j will be the second column of our rotation matrix. So we go ahead and rotate this, and we're going to get another right triangle, but in this case, I actually need to draw the perpendicular from the endpoint of f of j across to the y-axis. And so I'll go ahead and draw that, because the angle theta is between j and here. And I want that angle theta to be inside the triangle. So once again, I just want to solve for the sides of this triangle. And again, the length of the hypotenuse is the length of f of j, which is the same as the length of j. It's a unit vector. It has length 1. So what I really need to do is figure out a and b. Well, by the exact same reasoning as before, a is the adjacent side, so its length is cosine theta. b is the opposite side, so its length is sine theta. Again, this works out nicely because the hypotenuse has length 1. Now the one part which might be a little bit confusing is, in this case, the components of the vector. Right? Notice that in this case, a is actually the height, so that's our second component, and b is the length, it's the horizontal component, but it's going in the negative direction on the x-axis. That's why we have negative b. So the first component is going to be the negative of this side length. That's why this time the output, the final answer, is negative sine theta, comma, cosine theta. So this is the image of the vector j. This is going to be the second column of our matrix. Putting it all together, we have our first column, cosine and then sine. So that'll be going up and down. The second column is negative sine and cosine. Again, second column going up and down. That leaves us with this, the rotation matrix, in 2 dimensions. It's cosine theta, sine theta. It's our first column, and negative sine theta cosine theta is the second column. So if you want to rotate a point in two-dimensional space by some angle theta, calculate these different values. That gives you a matrix, and you can multiply your vector by that matrix. So hopefully this makes sense. And if so, then we can move on to rotating in 3 dimensions. It's a little bit more complicated for a couple of different reasons. First, rotations in 3 dimensions, we rotate around an axis, not just a single point. There's a lot more types of rotations we can do. Right? In the 2-dimensional case, we really were only interested in rotating around the origin point. But in 3 dimensions, you could rotate around the x-axis, you could rotate around the y-axis, you could rotate around the z-axis. And it turns out, if you think about 2-dimensional space, right, the xy plane, you could think of that as being embedded in 3-dimensional space. Right? The xy plane, think of that as the set of points where z equals 0. So you could actually think of rotating around the origin, right, rotating in this direction. Think of that as rotating around the z-axis. Right? So the work we did doing that calculation in 2 dimensions actually turns out to be helpful for calculating a rotation in 3 dimensions. One useful fact, which is worth mentioning, because it's going to save us some work later, if you rotate around an axis, you're not moving that axis. Just like when we rotate around a point in 2-dimensional space, the origin, well, that doesn't get moved at all. And similarly, rotating around an axis does not change the axis. Now, in theory, you could rotate around any vector that you wish, but we're only going to derive formulas for rotating around the x-axis, the y-axis, and the z-axis. Some combination of these 3 could give us any rotation that we want. Our strategy is going to be the same as before. We know that rotation is a linear transformation, so we're going to just figure out what happens to the 3 standard basis vectors. What happens to I, j, and k in each of these cases for each of these different types of rotations. Once we figure out what happens to those vectors, then we'll know what the columns of the matrix are. Again, our goal is to get 3 rotation matrices corresponding to rotation around each of these axes. So we'll start off with rotation around the z-axis because we've actually done most of the work for that already. Right? So again, we know that rotation around the z-axis fixes the z-axis. Right? So that means that the basis vector k, which is 0, 0, 1, does not move. F of 0, 0, 1 is equal to 0, 0, 1. And that gives us the 3rd column in our matrix. We know that the z components, again, will not change. Right? So f of I, remember I is 1, 0, 0. That last 0 in the z position does not change. Same thing here. So j is 0, 1, 0. Right? That z component is not changing. So we know these entries. And we know what happens to the x and y values when we rotate around the origin, or the z-axis. Right? It becomes cosine theta, sine theta. That's our first column. And negative sine theta, cosine theta, that was our second column. Right? In fact, if you look at this upper 2 by 2 submatrix, it looks just like rotation in 2-dimensional space. Right? It's just we're extending it to 3 dimensions. So if you want to rotate a point around the z-axis by some angle theta, you can calculate the values of these trig functions, and then multiply your point by that matrix. And that will tell you where your point moves to. All right, that's rotation around the z-axis. Rotating around the other axes is really quite similar. And that's why if we have a good understanding of 2-dimensional space, we can kind of bootstrap ourselves and understand what happens in 3-dimensional space. So rotation around the z-axis, the changes are so subtle you might not have noticed that I switched slides from the z-axis to the x-axis. This is very similar to our previous work. Right? You could draw a very similar diagram, but instead of having an x-axis and a y-axis, right, since we're going to rotate around the x-axis is fixed, so we really only need to know what happened during the y-axis and the z-axis. Right? Those are the two complicated ones. We know that f of I, since the basis vector I lies along the x-axis, and that x-axis stays fixed, we know that f of I is equal to I. Right? I is the vector 1, 0, 0. That stays as the vector 1, 0, 0. And that gives us this column of the matrix. For the other two vectors, right, again, f of j and f of k, that lies along the y-axis and the z-axis. And it's going to be a very similar diagram to what we had before. And if I flip back to an earlier picture, again, imagine that this x is a y. Imagine that this y is a z. Imagine that this I is a j. And you get basically the same result. Right? You'll get that first point, the 1, 0 at the end of the vector j, 0, 1, 0, moves to 0, cosine and sine. And again, the 0 is fixed because points on the x-axis are fixed by this kind of rotation. Similarly, k is 0, 0, 1. The first 0 is the fixed x component. The final 0, 1 becomes negative sine cosine. Right? So that gives us the third column of our rotation matrix. F of j is the second column, and f of k is the third column. And once again, notice that here in the lower 2 by 2 submatrix, it looks like our two-dimensional rotation again, which it kind of is. All right, so that's rotation around the x-axis. Rotation around the y-axis, hopefully it's not a surprise, is going to be very similar. Right, so again, rotation around the y-axis fixes the y-axis. So the basis vector j, which is 0, 1, 0, stays the same. That gives us the second column right here. And the y components are going to stay fixed. That gives us these two zeros in these positions. Now, you might be a little bit surprised at the order of things. Right? It looks a little bit different than before. Right? We have a cosine and a negative sine and a sine and a cosine. And why are these in this slightly different order? Right? Doesn't the negative sign go up here? The answer is, in this case, we have to remember the orientation of the axes. Right? So if you remember, in three-dimensional space, we think of x as going left and right. We think of y as going up and down. And z, consider that as kind of coming out the screen right at you. Right? That's the z-axis. So if we try to draw the same diagram as before, and we're looking along the y-axis, right, the positions of some of the vectors are going to be a little bit different. So if we go back to this one, for instance, let's say instead of x and y, let's make this x and z. Right? In that case, we want to consider, we're talking about rotation around the y-axis. That's why we label this as x and z. Which direction would y point at? Right? Does y come out of the screen at us, or does y go into the screen? Right? And the answer is y actually goes into the screen because of the orientation of the axes. So again, if this is x and this were z, y would go into the screen. Rotation, counterclockwise rotation around the y-axis, right, would actually appear to be going in the opposite direction. Right, so the diagrams, the angle theta would actually appear below the axis in this case. So what's happening with the rotation around the y-axis, right, the reason for these different negative signs is because of the perspective that we're taking when we draw these diagrams. It's like all the different thetas were negated, but cosine of negative theta, well, that's still cosine of theta, since it's an even function, and sine of negative theta, that actually reverses the values here. So this doesn't make sense. I highly recommend trying to draw out a diagram, or we can just take my word for it. And this is what rotation matrices are going to look like for the x, y, and z axes. Right, and so far, we're doing pretty well with our different transformations. It takes a while to derive the rotation transformation, so we'll save the translation for the next video. But we're almost there.